Hello world. All right, this is our chapter 4 in physics. We're going into motion, and we're talking about speed and motion. Starting off, motion is relative. An object is moving if its position relative to a fixed point is changing. You can describe the motion of an object by its position, speed, direction, and acceleration. Once again, relative to a fixed point of reference. So even if things appear to be at rest, they move. And they typically will move if you change your point of reference. So what do I mean by a point of reference? Let me go on. A book that is at rest, relative to the table it lies on, is moving at about 30 kilometers per second relative to the sun. So if we see the sun as a fixed point of reference, everything on our Earth is moving with the Earth at 30 kilometers per second relative to the sun as it orbits the sun. The book moves even faster relative to the center of our galaxy. As we know, the entire galaxy is rotating. So relative to that imaginary point at the center of the galaxy, that's probably a black hole that we can't necessarily look at directly, but we can observe indirectly. Relative to that, we're moving even faster. Another example is the Indy 500. So relative to the track, the cars are moving, but they're going in a circle, and so they're not necessarily undergoing any displacement because they're constantly each lap going back to their original position. When we discuss the motion of something, we describe its motion relative to something else. So the space shuttle, for example, is moving at 8 kilometers per second relative to Earth below as it accelerates out of our atmosphere. A car racing on the Indy 500 might reach a speed of 300 kilometers per hour relative to the track. Unless stated otherwise, the speeds of things in our environment are measured relative to the surface of Earth. So for example, the speed limit. When they tell you the speed limit is, say, 65 miles an hour, they're saying 65 miles per hour relative to the Earth, relative to the surface of the Earth. That's the way the law is written. They don't explicitly call it out in traffic signs, but that's what they mean. Although you may be at rest relative to Earth's surface, you're moving at about 100,000 kilometers per hour relative to the sun. A hungry mosquito sees you resting in a hammock in a 3 meter per second breeze. How fast and in what direction should the mosquito fly in order to hover above you for lunch? Interestingly, this is similar to drones. If you've ever played with quadcopters or drones or anything like that, you'll notice that if you're in a wind, it's very hard to maintain a position unless you completely fly against the wind in the exact direction that the wind is coming at you. And so you'll have to balance that velocity vector in an exactly equal and opposite direction. And so as the answer says here, the mosquito should fly toward you and into the breeze. When above you, it should fly at 3 meters per second in order to hover at rest below you or at rest above you. In other words, the mosquito is going to have to completely cancel that velocity vector, and it should have an opposite direction equal in magnitude velocity in order to do so. How can you tell if an object is moving? I mean, unless it's accelerating, you can't really sense it. Like if you're on an airplane flying at, say, 600 miles an hour, or whatever the airplane flies at, you can't tell you're moving unless you're being accelerated. So unless there's turbulence, unless you're moving up and down and bumping around, you can't really tell. You can flip a coin as though you were standing stationary on the ground. You don't really see, you can't observe that constant motion that you feel when you're in an airplane. Just like with the Earth, you can't feel yourself going at 100,000 kilometers an hour around the sun. We can observe that things are changing like seasons and things like that, but we don't really observe our apparent position to the sun, relative to the sun. Just like we can't feel the Milky Way galaxy. We can't feel our solar system orbiting the Milky Way galaxy. We can't feel the Milky Way galaxy being flung toward the Great Attractor. Those are things that we can't really observe, that constant velocity. And yes, even though it's a curved path, it's still a straight line path along the curvature of space-time, and that's a conversation for another day. Anyway, speed. You can calculate the speed of an object by dividing the distance it travels by over the time that it takes to travel that distance. In other words, distance divided by time. Like think about the speed limit. If the speed limit is 65 miles per hour, distance is 65 miles, time is per hour. Also note that that's your instantaneous speed. They're not necessarily saying your average speed can't go over 65 miles an hour, because if you start off going really slow, you can have some peaks well over 65 miles an hour and still not average out to over 65 miles per hour. What they're saying the law is you cannot have an instantaneous speed at any time over 65 miles an hour. And your speedometer reflects instantaneous speed. So before the time of Galileo, people described moving things as simply slow or fast. Such descriptions were vague. Galileo is credited as being the first to measure speed by considering the distance covered and the time it takes to cover that distance. So speed is how fast an object is moving. Some different ways to express speed include miles per hour, kilometers per hour, centimeters per day, light years per century. Some of these are kind of weird. Other ones you can kind of understand if you're thinking about plant growth. Right? Plants don't grow in miles per hour. That'd be really hard to gauge. But you could probably say, on some fast-growing vines, they might grow a centimeter or more per day. Some trees. Cheetahs, they're pretty fast. Cheetah is the fastest land animal over distances less than 500 meters. And ask yourself this, wait, why are we saying less than 500 meters? Because this explosive speed of a cheetah can't be sustained for very long. This is an anaerobic workout for them. But their muscles are such that they can store enough oxygen to be able to metabolize energy for that distance. And they can achieve peak speeds within that distance of 100 kilometers per hour, which is roughly 60-ish, 62 miles per hour or so. We will primarily use units in physics of meters per second. So typically this is what we'll use. We won't be using miles per hour. We'll be using meters per second. If a cheetah covers 50 meters in a time of 2 seconds, its speed is what? Distance over time. You can look at the units here. Meters over seconds. So if we take the meters and divide by the seconds, 50 divided by 2 gives us 25 meters per second. We take meters divided by seconds, and that gives us units of meters per second. Here's a table of approximate speeds just as a reference point. So bowling, typically, you're probably bowling around 12 miles an hour. And if you go to some bowling alleys, they'll actually tell you your bowling speed. And I've noticed that if I use a heavy ball, I'm probably bowling close to 12 miles per hour. But if I get a really light ball, my speed is much higher. And when we talk about kinetic energy, you'll understand why. Because each throw, you're roughly giving it the same amount of kinetic energy. But what's going to change is how fast you can throw it. Anyway, a really good sprint would be about 25 miles an hour. It's a very good sprinter, which is about 11 meters per second. A sprinting rabbit might be around 37 miles per hour, which is around 17 meters per second. A tsunami, don't want to try to outrun that. 50 miles an hour or 22 meters per second. Sprinting cheetah we just talked about, 62 miles an hour or 28 meters per second. A batted softball, 75 miles an hour, and a batted baseball about 100. It's pretty fast. You wouldn't want to get hit by that ball. So we talked about instantaneous speed just a moment ago. Your car does not always move at the same speed. Sometimes you're stopped at stoplights, sometimes you're on the freeway, sometimes you're going through residential neighborhoods, and hopefully you're obeying the speed limit, and your speedometer in your car is going to reflect your instantaneous speed. So like it says here, the speed at any instant is called the instantaneous speed. Typically when you're calculating instantaneous speed, you're taking the limit as your distance is approaching zero of the, as the time is approaching a duration of zero, that time interval is approaching zero, and you're trying to calculate how much distance you traveled in that infinitesimal amount of time. As you take that limit, you'll understand something that you do in calculus called an integral, but we're not going to go into detail on that because this is not a calculus-based course. So just understand that when we say instantaneous speed, we're just trying to figure out how fast you're going at that instant in time. So your speedometer in your car, like I said, is going to be giving readings of instantaneous speed. So apparently your speedometer can do calculus. You'll notice that the numbers on the outside are miles per hour, and the numbers on the inside are kilometers per hour. Kilometers per hour on the inside, miles per hour on the outside, and you can see that in the middle. Just the bolded white numbers are the miles per hour, and the lowercase, I don't know if it's lowercase numbers, that doesn't make any sense, but you get the idea. That color of kilometers per hour reflects that color of numbers. In a trip by car, the speed will certainly not travel. So, oh my gosh, I can't talk. The car will certainly not travel at the same speed all during the trip. Like we talked about, sometimes you'll be speeding up, sometimes you'll be slowing down, and your average speed is the total distance covered in your trip divided by how long it took you to travel that distance. So like, for example, if I travel all the way out to Santan from Queen Creek, I can calculate how far I traveled and how long it took me to get there to figure out my average speed during that whole trip. So maybe sometimes I'm traveling through residential neighborhoods at 10 miles an hour or whatever the speed is around the school, and then I might go on to roads that are like 45 or 50, and so I'm going to get some average speed in between those, and you just basically just take the distance divided by the time it took you. So here's a calculation. For example, the distance of 240 kilometers during a time of 4 hours, your average of that would be 60 kilometers per hour, and that's simple math. Okay, in the numerator you have 240 kilometers, in the denominator you have 4 hours. Sorry, 240 kilometers, yeah, that's what I said. 240 kilometers divided by 4 hours, that's going to give you an average speed of 60 kilometers per hour. And notice if we don't include the direction in our answer, we're giving a speed. If we have a direction and a magnitude, then we have a vector. Something to note. Okay, we talked about that. Okay, so here's a fun one. If a cheetah can maintain a constant speed of 25 meters per second, it'll cover 25 meters every second. So if it maintains that speed for 10 seconds, how far will it have traveled? What if it maintains that speed for 1 minute, which is 60 seconds? And that should be pretty simple math. Okay, in 10 seconds, it'll have traveled 250 meters. In 60 seconds, it will have traveled 1,500 meters. The speedometer in every car also has an odometer. An odometer is going to record the distance traveled. And note that distance is different than displacement. Distance is literally how far you've gone, and displacement is how far you are from where you started. So if you're going around a track in circles, every single time you do a lap, you just decreased your displacement down to 0 because you're at the starting point. A joke I made is that if you die in the same place you were born, then your lifetime displacement is actually 0 because you died in the same place you were born. You started where you left off. You started where you began, I should say. If the odometer reads 0 at the beginning of a trip and 35 kilometers a half hour later, what is the average speed? So we know here that in 30 minutes or in half of 1 hour, we've traveled 35 kilometers. So if we maintain that same exact speed for a full hour, we'll have doubled our distance. And you can just simply do that math in your head, right? If we travel 35 kilometers in a half hour, then we'll have traveled 70 kilometers in a full hour, which is our average speed, 70 kilometers per hour. You can also do this mathematically just by dividing by 0.5, which is the same thing as multiplying by 2. So if you divide by 0.5, 35 kilometers divided by a half hour is going to give you 70 kilometers per hour. And note that whatever goes into your quotient is going to come out. So if you put in kilometers per hour, you're going to get out kilometers per hour. If you put in kilometers per second, you're going to get out kilometers per second. Don't forget that, because if I'm asking you for kilometers per second and you're using kilometers per hour, you're going to have to convert hours to seconds or vice versa. So pay attention to what you're putting in and realize that those units are going to come back out. Okay, so that's speed. We talked about how velocity is a description of speed and the direction that it's moving. So very similar to speed. The only difference with velocity is we are specifying which direction we're moving. So like it says here, a car can be moving at a speed of 60 kilometers per hour. But if we include the direction, we're now saying its velocity is 60 kilometers per hour to the north. And so it's no longer a speed, it's now a vector because we've included the directional quantity. A quantity such as velocity that specifies direction as well as magnitude is called a vector quantity. I'm going to go ahead and stop here at 4.3, and I will pick up where I left off in potentially another video. So thank you for watching. Don't forget to subscribe.